Have you ever wondered why something that seems so simple becomes so difficult in the classroom? Today, we're uncovering the science behind it. Welcome to This Explainer. We're going to look closely at how our brains process information and really why the way we learn might be fundamentally shifting. Imagine asking a classroom full of students one simple question: what is 7 times 8? For some of them, the answer just fires off instantly: 56. But for others, they completely freeze. Total panic sets in. You know that feeling, right? Their mind goes completely blank, and some might even secretly reach for a calculator hidden under their desk, just to be absolutely sure. But here is the really strange part. Many of these exact same students, the ones freezing over a basic multiplication prompt, can spend hours, literally hours, solving highly complex, multi-step puzzles in video games. They show this incredible stamina and problem-solving ability at home. So what changed? Did these students suddenly lose their intelligence the moment they crossed the classroom threshold? No way. Or has something much bigger changed about the way modern brains are actually learning? Let's dive into this. And the first step is breaking down a pretty massive myth. Most people kind of think math is just about numbers. Society often treats it as just calculating, getting the correct answer as fast as humanly possible. But actually, math is about reasoning. It's a language of patterns. It's all about memory and constructing mental schemas. The numbers, they're really just the alphabet of that language. I mean, imagine trying to learn English by just memorizing the dictionary without understanding how words form sentences. That is exactly how math feels when students memorize formulas without understanding why they actually work. To truly understand why students struggle, we need to look at what educational researchers call the hidden brain problem. It's rooted in this foundational concept called cognitive load theory. The basic idea here is that our human working memory, essentially the mental scratchpad we use to process information right in the moment, has a strictly limited capacity. If a learning task requires too much of that capacity, learning is completely hampered. Think of it like a computer trying to run way too many heavy applications all at once. Eventually, the whole system just resets. Now, cognitive load theory breaks this brain drain down into 3 distinct types. First up, we have intrinsic load. This is just the inherent difficulty of the subject matter itself. Some concepts, by their very nature, require more cognitive resources to process because they have high element interactivity. That basically means you have to hold several different pieces of information in your head just to understand how they relate to one another. You can't magically make advanced geometry as simple as basic addition, right? The inherent difficulty is fixed based on what the learner already knows. Then we have our second type, extraneous load. And honestly, this is the bad stuff. It's the unnecessary mental strain caused by poor instructional design, confusing layouts, or just constant interruptions. Think of split attention tasks where you're forced to look back and forth between a complex diagram and a dense block of text, or trying to listen to a teacher while a screen flashes totally unrelated information. This rapid switching completely shatters your working memory, leaving far fewer resources for the actual learning. Finally, we get to germane load. Now, this is the cognitive effort we actively want. It's the mental heavy lifting used to build and automate understanding, a process researchers call schema construction. When you are actively connecting new information to things you already know, classifying patterns, and inferring rules, you are applying germane load. It is the good effort, where true, deep learning happens, and those mental connections are finally solidified. So the crucial takeaway here is that we absolutely need to maximize germane load while minimizing extraneous load. But let's consider the modern world our students live in. They are bombarded by constant push notifications, a never-ending feed of short-form videos, and rapid app switching. Our brains have become incredibly efficient at consuming tiny bites of information very quickly. But mathematics? Mathematics requires slow thinking. It requires deep concentration to hold several ideas in mind all at once. Imagine trying to solve a complex problem while someone keeps interrupting you every few seconds. Every single digital interruption makes that process infinitely harder. And this intense battle for attention spills directly into the classroom. Many classrooms today operate in an environment heavily pressured by limited time, massive curricula, and high-stakes standardized testing. It basically becomes a race to the finish line. Lessons move fast, and students are given this artificial time-critical pressure where getting the answer quickly is prioritized over thinking deeply. But here's the secret. Good mathematicians actually spend most of their time thinking, not calculating. Because of this fast-paced structure, we run into a major architectural problem. You see, math is exactly like building a staircase. If a fast-paced lesson causes a student to miss just one foundational step, the climb up the rest of the staircase becomes much, much harder. That single misunderstanding, that one overloaded moment of working memory, gets carried right into every future lesson, completely compounding the cognitive load. And that is exactly where something unexpected and honestly deeply painful happens. Students look at their struggle, they feel their working memory completely overloading, and they reach a totally false conclusion. They begin believing they simply aren't math people. They internalize the structural failure of an overloaded working memory as a personal failure of their own intelligence. Well, let's definitively debunk that right now. The idea that intelligence is fixed at birth, that you're either born a math person or you aren't, is a complete myth. There is zero scientific evidence for it. The reality is that brains change, neural connections strengthen through practice. The students who improve the most in math aren't always the fastest calculators. They're often the ones who simply continue asking questions. They understand that making mistakes is literally how you build understanding, one connection at a time. Now, for the educators and instructional designers tuning in, educational research reveals an absolutely fascinating phenomenon called the expertise reversal effect. When a learner is a complete novice, they're highly vulnerable to memory overload. They really need integrated, worked-out examples to minimize that extraneous load. But as that learner becomes an expert, those exact same step-by-step guides actually become a distraction. Experts need conventional problems, where the guidance naturally fades away. It proves that teaching must dynamically adapt as a student's brain builds those complex mental schemas. So, what does this actually look like in practice? Well, around the world, great teachers are totally changing the game. Instead of just asking, "What's the answer?" they ask, "How did you think about it?" They have students draw visual models to help offload working memory. They connect abstract concepts to real-life examples. And maybe most importantly, they celebrate mistakes as vital learning opportunities. They are actively reducing that unhelpful extraneous load and massively boosting the powerful germane load. Because here is the ultimate truth. When students understand why, the formulas finally make sense. Research consistently shows that conceptual understanding beats rote memorization every single time. It's really about taking those abstract mathematical puzzle pieces and fitting them together into a connected mental framework. When you can see the full picture, you don't have to memorize every single pixel. Remember that student we talked about at the very beginning? The one who froze at 7 times 8? The problem was never their intelligence. Maybe, just maybe, no one helped them see the pattern behind the numbers yet. Because math isn't a talent, it is a language. And struggling to speak it doesn't mean you're broken, it simply means your brain is still building the connections to become fluent. So, my final question to you is, will you help build those connections? Whether you're a teacher fostering confidence, a parent offering patience, or a learner continuing to ask questions, just remember that sometimes the hardest problems truly teach us the most. If you believe education should empower understanding, not just memorization, make sure to subscribe to MindSparkEd. Join us as we continue to make the science of learning visible. Thank you so much for exploring this topic with me, and I'll see you in the next explainer.